This is a short video just to recap some of the ideas related to resource competition theory. And we'll begin by looking at a couple of panels that illustrate the main concepts behind resource competition theory. In particular, though, we're just looking at one species on its own right now, utilizing a resource that's available to it, basically a food source, for example, that it's consuming. The panel on the left is looking at the resource density on the x-axis, going from low to high. And on the y-axis of that same panel, we're looking at the per capita rates of the species that's consuming the resource. In particular, we have the solid blue line representing per capita birth rate, and the dashed black line here illustrating the per capita mortality rate of that species. Note that we're assuming the mortality rate is independent of resource density, of availability of resources. By contrast, we're assuming that the per capita birth rate is a function of resource availability. We can identify a couple of different regimes, if you like, in this panel. By noting this particular value R star, we see that when the resource is at a density below R star, the species per capita birth rate is below the value of the species per capita mortality rate. And so we would expect that species to be in decline. Above the resource density of R star, we see that the per capita birth rate actually exceeds the per capita mortality rate, and we'd expect that species to therefore be growing at reasonably high levels of resource availability. However, as it grows, the species is going to be consuming more and more of that resource, and we'll actually see the resource density decrease. And eventually, when it decreases down to this level R star, the whole system is in equilibrium at that point. We've got the per capita birth rate and the mortality rate equal, and therefore the population size is no longer changing, and therefore the consumption rate of resource is constant over time. That's illustrated a little more clearly on the panel on the right. We start this system with one species again, and the resource, which is shown in green. We start with a reasonably high amount of resource. Over time, that's being consumed by the species, and so we see the resource dropping. Meanwhile, the population is itself increasing. The species that's consuming the resource grows up towards effectively a carrying capacity, at which point the resource level is only sufficient to maintain the population, not to increase it any further, because we're now at this point R star, where the mortality rate is equal to the birth rate, and so the population stabilizes, as does the resource level. So that's one species on its own. If we consider two species that both use this resource, we can illustrate that by adding some lines into these two panels. So back to the left-hand panel, we've now introduced species B to go alongside species A, and we see that they have different mortality rates, with species A having a higher mortality rate than species B. And we see that they have different per capita birth rates that change in response to resource availability. The general trend is the same, however. It's just that the numerical values are different between them. We note that species A has a higher R star value. So if we think about the system over on the right-hand side now, being at a high resource state, initially that's good news for both of the species. There's plenty of resource availability. Both species have their per capita birth rate higher than their per capita mortality rate, and so both species are growing, and that's what we see initially on the right-hand side as the blue and the orange curves increase over time. However, while all this consuming is going on, the resource density is decreasing, and we actually first hit the point R star of species A. So as the resource depletes, we first pass through R star A, and at that point species A only has enough resource to maintain itself, but we're still in a regime where species B has a higher birth rate than it does a mortality rate, and so species B is still growing. That means that we're still going to see the resource level drop because the species that's consuming it is growing even larger. And we then enter a regime where the resource level is between R star A and R star B. At that point, now species B is still growing with its per capita birth rate higher than its mortality rate. However, species A has a higher mortality rate than it does its per capita birth rate. And so we see a regime now on the right-hand side with species A in decline towards extinction, species B continuing to increase, all the while the resource still being depleted by this ever-growing population of species B. Eventually, the resource drops to the level R star B, at which point species B is only just able to maintain itself. But now it doesn't really have to worry about its competitor species A. It's for a long while been in a regime where its mortality rate is higher than its birth rate, and it's on the way out to extinction. And so what we'll see happen is species B will maintain itself, will grow to a reasonably high carrying capacity, and the resource will stabilize to a low but sufficient level for the population to persist, whereas species A has lost out because it had a high R star value. And so one of the points to take home from this is that the species with the lower R star value is the one that's going to win out in this competition scenario. We can actually see some evidence of this having been played out for real. In particular, interspecific competition between two different diatom species for a silicate resource. And so here we have the two species, A. formosa and S. ulna, both competing for silicates. This is a situation that plays out in the lakes up in Lake Michigan. The diatoms are planktonic algae, and they form the basis of food webs, and so it's been a well-studied system. Here we note that both of the populations are able to grow. We see these solid black lines here. This is A. formosa on the left-hand side, increasing its density and eventually effectively leveling off to a constant density. All the while, the silicate resource shown in the slightly thinner black line here is decreasing down to a low but non-zero value there. On the right-hand side, we see a similar situation for S. ulna. In these panels A and B, the two species are competing are not competing with each other. They just have access to the resource by themselves. And we note that S. ulna also grows up to a significant and stable level, and the resource gets depleted. We note, however, hopefully it's relatively clear from these diagrams, that the silicate concentration, which is on this second y-axis in both the panels, is actually lower on the right-hand side for S. ulna. So it's able to grow even when the concentration of silicate is very, very low. And that's quite a lot lower, it's a little hard to see here, than was the case for A. formosa. And so in this case, S. ulna has the lower R star value. And we would predict, according to the theory we just looked at, that if these two species were competing together, we would expect ulna to win out in that competition. Well, that is exactly what was investigated by Tillman in 1982. And in a series of experiments, we see that both of these diatom species are existing together with the silicate resource. And in all of these cases, of course, the silicate concentration drops quite significantly. And we note that it's S. ulna that grows and maintains itself at this relatively low resource concentration. It's not enough, it's not a high enough concentration for the other species to maintain itself. And so in all three of these experiments, we see S. ulna winning out, just as we predicted from R star theory. Another example of this, just to illustrate the some of the subtleties in what we mean by winning out and using these resources, we can learn a little bit more by studying some invasive Batellaria species that's replacing the native Cerathidia species along the mudflats of California. And this is work done by colleagues of ours at the University of Georgia, particularly Jeb Byers. And what these authors did was they considered that the growth rate of either of these species is basically determined by births and deaths, and they assume that there's a per capita mortality rate, M sub n, and that's true for the native species we're illustrating here. There's also the birth rate or the growth rate of these species, and that's going to boil down to a combination of these three per capita rates: alpha, epsilon, and R. Alpha is the consumption rate of the resource. Epsilon represents the conversion efficiency, how well a species does at turning a resource into survivorship, reproduction, effectively population growth. And then the big R here represents the density of the resource that's available. So those three things combine to really determine the population growth rate. If we set that equation equal to 0 and think about the resource state at that point, we can just manipulate these equations, just rearrange them to see that the R star value at equilibrium is actually given by the ratio of the mortality rate in the numerator to the product of the consumption rate and the conversion efficiency in the denominator. If we think about what that means for two different species, so now we've got our native, all with subscript n, and our invasive species with subscript I. We know from our previous slides that the species with the lower R star is going to win out in competition for a common resource. And so now we see that for the R star of the invasive to be lower than the R star of the native species, the inequality at the bottom here has to be satisfied. And that's an interesting expression just to pause and take a look at, because it tells us that the R star for the invasive species can be smaller for a variety of reasons. It will be small if its mortality rate is low, in other words, if it's a relatively long-lived species. And it'll also be small if the expressions in the denominator are large, in other words, if it's a relatively fast consumer of this shared resource, or if it's relatively better at converting that resource into energy and offspring. And so we see that there are multiple ways in which an invasive species can win out. If we follow through the results of this particular study system, the resource that they're sharing is a diatom, and in a series of experiments where the authors looked at different snail densities, regardless of which snail density you look at, there really isn't much difference between the consumption rate of the diatoms between the two species. That's the alpha expression that we just looked at on the previous slide. That doesn't seem to be dramatically different and doesn't seem to be able to tell us too much about which species is likely to win out. However, given a relatively consistent consumption rate between the two species, the actual growth rate of the invasive species, Batellaria, is significantly higher. And so for the same amount of consumption, it's doing better at turning that into population growth. And so actually individual growth, which is also going to lead to survivorship and high fecundity, and so it's going to translate into population growth. Here we see a big difference now between the conversion efficiency, so not the consumption rate alpha, but rather the conversion efficiency epsilon, a lot better for the invasive species. And actually on these mudflats, certainly in the northern extent of the natives range, this invasive does seem to be winning out in a competition here. I haven't actually shown a panel on this, but in addition, the mortality rate of this invasive species is significantly lower, so it's a much more long-lived species as well, so it has this extra advantage, which helps to explain, as we can see here, why the native species over time has been in decline in certain regions where they co-occur, and the invasive species is really taking off and taking over. And so hopefully This recap has pointed out some of the main ideas about R-star theory, its ability to predict which species is likely to win when there's